Hello there, math analyzers. Welcome to your Chapter 7, Lesson 3 notes. We are going to solve exponential equations. But before we do, we have got to understand bases raised to powers, okay? Now, the cool thing about the first part, just going to do some exponents, equivalencies, right? Anything to the 0 power is 1. So any base that I raise to the 0 power, I get out a 1. Now, you'll notice that then I start raising to bases, and whoa, raising bases to powers, we get increases real quick as far as their equivalencies, right? So, like 4 to the 4th power is 256, 6 to the 4th power is 1,296. We get real quick into some of these big integers, okay? Okay. So, how does that work when it comes to equations? Well, let's think about that. An equal sign means that both sides are the same. Both sides are the same amount. Both sides are the same value. Okay. And what you're doing is you're figuring out what's going to plug in for my variable and make that happen every time. So, the rule for solving exponential equations is that if you have the same base and they're being raised to powers, then the powers must actually be equal to each other. Which, doesn't that make perfect sense? Okay, doesn't that make perfect sense? If you have 2 raised to the 3x plus 5 equals 2 raised to the x, then those two things are equal to each other. Those two exponents actually are the same, and we've got to find that x value that makes that happen. So all we would have to do is take the exponents and solve that. And that's what we're going to do. We're going to take the exponents, and that's what we're going to solve. So I'm going to give you a whole bunch of exercises here that I'm going to do, already have done off to the side in an explanation, but I'm going to do them in front of you so you have an idea of what these things look like. So my exercise 1 is solve 2 raised to the 3x minus 1. Didn't I just say that? I wasn't even thinking this problem. Equals 2 raised to the 5th power. Well, there's actually only an x over in this exponent, but I have exactly the same base. So that means these exponents must be equal to each other. So that's actually the only equation I'm going to solve. So I just bring my exponents down in their own little equation and solve it. Add 1 to both sides, you get 3x equals 6. And divide both sides by 3, you get x equals 2. Let's think about that. 3 times 2 is 6. 6 minus 1 is 5. 2 to the 5th equals 2 to the 5th. There you go. Now let's say the other side does not have the same base. The reason I listed all those exponential equivalencies above is so you can try to find the same base out of two numbers. Now, the part about this that's difficult for people is remember that this has to result from 2 to a something power. Okay, because you're trying to get that base to be smaller because you're putting an exponent on it so that the exponents can then come down and be the equation set equal to each other. So that's why I have this list up here. So you can go and you can say, well, 2 is the base that I have down there. Let's find something 2 to the something power where the result is 32. So what I do is I snag this equivalency right here. And I say, if 32 is equal to 2 to the 5th, and I've got a 32 right here, and I want a 2 as my base, I'm going to substitute 2 to the 5th power right here for 32. Now this side already had 2 as a base, so I just bring it down, and oh look, now I've got the same base. I can set the exponents equal to each other. And yes, I know this is the problem from above, so this is a nice quick, we already know it's 2. But I was just showing you the progression, right, of potential problems that we will look at. X, when we get the answers for our variable in these, they have a tendency to be really small integers or fractions. Okay, as far as exponents go, because we're not going to have 100 as an exponent in these things, right? That does not happen very often. So I'm just kind of giving you a heads up. These have a tendency to give you fractional answers a lot. It's not a bad thing. We just learned that fractional exponents are just radicals anyway, so it's fine. Oh, this comes back to the very first thing I said to you. Anything to the 0 power is 1. So if I'm looking at one of these equations and one side is a 1, go to the other side, look at whatever its base is, and say, well, I need 7 as a base, right? So let me just do 7 to the 0 power to replace 1, and boom, I'm all set. Now I can just bring these down. X minus 3 is equal to 0. So add 3 to both sides. X equals 3 is my answer. And if you think about that, 3 minus 3 is 0. 7 to the 0 is 1. It checks. So the great thing is if you run into a 1 in one of these, you have it made because you just take the other base and put a 0 on it and you're good to go. Now, people get confused when the fraction is involved, but remember that fractions can come from a negative exponent. So just think about 2 to the what power gives me 16. So how could I get 1/16? Negative 4, right? 2 to the negative 4 is 1/16. So let's do that. Let's replace 1/16 with 2 to the negative 4 power. Now I have the same base, so I take their exponents and I set them equal to each other and solve. Divide both sides by 2, I get x equals negative 2, which if I plug in here, 2 times negative 2 is negative 4, and 2 to the negative 4th is 1/16. Boom, it checks. By the way, you don't have to do these checks. I'm just using them as examples to prove to you how I'm getting this stuff to work. Okay, how I know for a fact that these are working. So I'm checking my answers. Okay, so far in all 4 examples, I have only had to change one base. But that's not always going to be the case because you can already see from our list, that there are not a lot of numbers that we can use to do this process, right? They have to come down to the same base. So if we're looking to try and come down to the same base, and I do mean come down to the same base, right? Well, then we've only got these options to be different sides, different bases that can convert, right? So if you're trying to get 3 as the same base, for example, it can only be one of these numbers or, 3 to the 6th, 3 to the 7th, 3 to the 8th, and so on. So as you can see, this is a very specific piece that we're looking at. You don't have to have these memorized. You always have a graphing calculator on you or calculator in general. You can figure these values out. So you don't have to memorize these by any stretch. I don't have them memorized, but I do have a general idea where I'm going base-wise, okay? And here's one of the things that gives me a hint about where I'm going base-wise. When I see 8, I can only get 8 from a base of 2 because 4 squared is 16, and I've already surpassed 8. So that means I have to use 2 on both sides. I can't just leave this as a 4. Just like if I see 9 and 27, right? I've got to head down to 3 as a base. Okay, because 9 squared is 81. I've already surpassed 27. So these are just like big hints that I know I can use to get down to much smaller bases. You're trying to get as small base-wise as possible. Okay, so both the 4 and the 8 need to convert into bases of 2. Well, 2 to the second power is 4, right? But this guy already had an exponent on it. Exponents rules, multiply. Multiply those together, which will mean distributing here in a second. 2 to the third power replaces 8. It did not already have any exponent other than 1, so I'm good on that side. But over here, now I need to distribute, so I get 2x minus 6 equals 3. Add 6 to both sides, you get 2x equals 9. And no, this won't divide evenly, but this goes into what I was saying, that most of these answers are small integers or fractions, and there you are. And I would leave it as the fraction form, just because the majority of the time, if you're running into multiple choices, they're in fraction form. This is it. This is what we're doing. This is how we're handling this stuff. Okay? It's not that bad. Let's do a couple more. examples, and then this is essentially what's on your homework, okay? So 6 and 36, let's get down to a base of 6. So this gets to stay. 36 needs to change to 6 squared, and then, of course, multiply by the exponent that was present, the 3x. So now that we've got the same base, just deal in exponents. So 4x plus 2 equals 6x. So notice I did that multiplication as I brought this down. Subtract 4x from both sides, you get 2x equals 2x, and divide both sides by 2, x equals 1. Makes sense? 7 and 49, so my base is 7. This side can stay. This side changes to 7 squared. And now just deal in the exponents. So since the bases are the same, the exponents must be equal. So that's what I actually solve. Subtract that 12 over, you get negative 6x equals negative 10. Divide both sides by 6. You actually get x equals negative 10 over 6, but that can reduce further. So let's go to negative 5. Positive, excuse me. What was I saying? Positive 5/3. Let me just write that up here. Negative divided by negative is a positive. There you go. Sorry about that. 9 squared is 3, right? Base of 3. So you've already got, change colors so you can see better. You've already got a base of 3 over here, no worries, but over here, it's a 2, and that needs to be distributed over the entire exponent that was already present. Now that you've got the same base, set the exponents equal to each other. Subtract 6x from both sides, so you get 4x equals 30. Divide both sides by 4, x equals 15 halves, 30 over 4. Both even. Like I said, small integers and fractions a lot of times. And also, like I said, there's very limited amount of bases you can use. 2 and 3 and 4 and 5 and 6 and 7 is like what we're trying to get down to here. Trying to get down to the lowest base. This already has a 5, and it's 5 to the first power, remember. If an exponent isn't listed, it's a 1. So now, let's see. Well, I know 5 squared is 25, but this is in fractional form, 1 over 25. So this is really 5 to the negative 2, and then, of course, we have to multiply by the exponent that was already there, which was our x. Negative 2 times x is negative 2x, and of course, that's a 1 over there, so divide both sides by negative 2, you get x equals negative 1/2. Again, very common with a fraction. Out of 4 I've done, 3 have been fractional answers. Oh, I can change that into whatever base I want, which is a 14, because I already have a base of 14, so booyah. Same base, set the exponents equal. Subtract 10, 2x equals negative 10, divide by 2, x equals negative 5. Back to a small integer. Okay, last but not least, fraction. 2 to the what power can give me 16? 4, right? So because I've got 1/16, it's really just a negative 4. So it's really 2 to the negative 4 power times the exponent that was already there. Over here, we did already have an exponent of 2, a base of 2. So we don't have to change anything. Now that we've got the same base, the exponents can be set equal to each other, and that's what we'll solve. So I'll just add 2x over here. So I get negative 2x equals 2. Divide both sides by negative 2, x equals negative 1. Very common, right? Small integers, fractions, typically as answers. Leave those answers in simplest fraction form, but you got this. This isn't too bad, okay? If you need any help with the day 2 practice, just let me know. There's old Regents questions, so doing some conversion when it comes to that. Actually, let me do this one real quick down here before I stop. So this is lesson 3, day 2. I just kind of continued to talk about this. And this is just a conversion happening here. But try these multiple choices. Okay, try those multiple choices so that you can, you'll just keep going with lesson 3. We don't need 2 days of it because we review anyway before our quiz. 16 and 64. 4 squared is 16. 4 cubed is 64. So how about we have a like base of 4? Okay, I'm going to do it over here on the left side. So let's replace 16 with 4 squared. And then, of course, multiply by the exponent that's already present. Let's replace 64 with 4 cubed and multiply by the exponent that's already present. So there's some distributing coming down to the next line. Once you got the like base, then the exponents are just set equal to each other to solve. So I get 4x plus 6 equals 3x plus 6. Whoa! Hey, oh, hey, I get x equals 0. Subtract 3x from both sides. Subtract 6 from both sides. X equals 0. Oh, that makes sense. Does it make sense? Some of you, when I started thinking about 4 to the second power and 4 to the third power, might have been saying 2 to the fourth power and 2 to the sixth power. Because 2 to the fourth is 16 and 2 to the sixth is 64. So could I have also done this problem using 2 as my common base? You betcha. So that's why I have this over here. So 2 to the fourth and then times the exponent that's already present equals 2 to the sixth times the exponent that's already present. And then I get 8x plus 12 equals 6x plus 12. And oh, I subtract this, I get 2x equals, subtract that, 0. X equals 0 is still my answer. Did it matter which of the common bases I used in that scenario? I got the same answer. That can only happen with certain numbers like 16 and 64. Okay, that's not going to happen like 4 and 16. You could make them a common base of 2 as well. Okay, so that's not going to happen frequently. That's why I did this problem when I saw it. That's not going to happen often at all. But if you happen to see my work and I had used a different common base, this is why. Most likely, if it's me, I've done both because I love doing it, right? Because it's so much fun. All right, guys. Good luck making those common bases. Again, do these multiple choices too with your homework, with your day 1 homework. No, homework number 1, do that. Make sure you're doing those. Practice that, and then we'll review lessons 1 through 3 next time. All right, guys. Good luck and have fun.